All right, I think everybody has had a chance to get their suite already, so we get started. Well, good afternoon, everyone. Welcome to the Mechanical Engineering Colloquium. We're very happy today to have a seminar given by Professor Seely Deng. I'm Ahmed Ghunaim. I think many of you know me already. So just a quick introduction for Seely. She did her bachelor degree in Tsinghua University in China. Following that, she came to the US. She joined Professor C.K. Laws at Princeton University to do her master and PhD in the general area of combustion, specifically focusing on low temperature flame chemistry. Following that, she went to Stanford to do her postdoctoral work for a couple of years, changing the subject a bit, moving towards solid reactions. Following that, she came to MIT, joined us as an assistant professor. Seely has had already a long career, although she's been here only 7 years, and she's had several awards, including the NSF Career Award and several awards from the Combustion Symposium, including Glassman Award, the Tsugi Award, and Bernard-Rousseau, right? Okay, so her general area of research is focused on developing and using machine learning approaches to improve combustion simulation and prediction, and that will be the topic of her seminar today. With that, Seely.
Thank you very much, Professor Gonian, for the introduction, and very glad to be here to share some of our recent work with the audience. So before I actually get started, I want to share an anecdote. So this is a picture I took over the summer. So my friend is leaving the state and transition to another place. So she left with me a potted plant, which I have no idea what that is, and just keep on watering it. And then all of a sudden, I noticed that after my summer trip, it has become a very healthy, I guess, a very tall one. And I have no idea how to take care of it. So I just pull out my phone and open up the app of ChatGPT and start to say something. My friend told me the name of this kind in Chinese. So I basically just mixed my voice saying, well, take a look at this picture and I have a name of this plant. So tell me how I should prune it, right, to make it healthy. And this is what ChatGPT spit out, which is quite impressive. Give me a mark, you should truncate it right there, and in Chinese. And so if you take a closer look at it, I'm not sure if it's the exact picture it takes. Probably there is some generative modeling for the picture, but it's pretty look the same. All right, so if we take a look at what happens during this practice, right, this anecdote, it's really the ChatGPT is taking information from both the images, voice, and across different languages, right? And at the end, it understands my need is how to prune my plant, and it gave me a solution. So what we want to do is that leveraging the expertise from domain knowledges from all the experts, right? And leveraging over the years our development on the modeling, on the theory, and on the experimental measurement. Can we come up with solutions to meet the energy crisis and try to model and understand energy systems and eventually to do the design and control of the energy system? And towards that, I'm going to share with you some of our recent work developing the so-called scientific machine learning and try to model and understand and be able to predict what's going to happen for general combustion systems, and with the hope that we can do active control and design of the combustion systems. So how we approach this problem is that if we think about it, we have the physical system, that's the combustion or engines that we want to design and control. We can perform some measurement on the system, and we can also try to utilize our experience, or hopefully from first principles, to understand that, right? So how do we have the fundamental knowledge about things? Is essentially in the mathematical world, we want to describe what's going on. We want to describe on the chemistry side what's going to happen from the fuel to oxidizers to the product, to the formation of emission species, right? And we want to understand how the flow, especially turbulent flow, is going to interact with the chemistry, right? So we need to have the crosstalk between the mathematical world and the physical world. So if we think about this, and then we can identify the opportunities that machine learning, especially scientific machine learning, can help us with. For example, if we have certain observations of the system, we want to be able to use that to guide us to come up with some mathematical models such that we can have this opportunity to model it in a reduced order way. So this type of problem, we can generalize it as the inverse problems. So essentially what I think machine learning could do is to help us do some tasks that we have been doing, which is through optimization, through regression, try to come up with a reduced order model to describe the physical world. After we have certain models, sometimes we need to calibrate the model parameters. Sometimes we just need to implement it in a numerical solver and to predict what's going to happen in the real system. So in this capacity, we actually need the computation to be very fast and to hopefully to the extent that we want to control the system, right? So in that case, I'm thinking for the machine learning side, we can really utilize the capacity in terms of representation, try to help us compute things faster, more accurate, and so on. And eventually, if we can build something called the digital twin, which I will talk later, such that we can predict what's going to happen to the physical system, we have a better chance to control that. So towards this, for the past 4 years or so, our group have conducted a lot of research tasks surrounding these forward and inverse problems, particularly trying to infer models from experimental measurements and try to fast forward the computations and be able to model the entire systems. In today's presentation, I'm going to pick 2 stories to share with you. Specifically, one on the inverse problem is that we want to see if we can predict the thermal runaway for lithium-ion batteries. And the second problem is showing you some of our recent work on trying to build digital twins to describe a combustion or general combustion systems. In terms of lithium-ion batteries, I don't think I need to emphasize the significance of that and the increasing trend in terms of deploying a lot of lithium-ion batteries for EVs as well as for grid storage, right? But we also hear about scary news about electric vehicles catching on fire, data center just catch on fire without any physical destroyal of the batteries, right? So not only we can mechanically abuse the system, such as introducing a crash to the batteries, but also by batteries just working on its own or even sitting there, there could be some self-heating process going on such that it can trigger the so-called thermal runaway and eventually trigger fires of lithium batteries. As we probably already know that lithium-ion batteries has many components. It has a cathode, anode, electrolyte, and also some intermediate species, such as the interface between the electrolyte and the anode, right? That's called the SEI interfaces. So actually, all of the components can undergo heat release processes under different conditions. For example, showing on the right is taken from the literature that so you have this interface between the electrolyte and the anode that's called the SEI layer that can become thermally unstable as low as 80 Celsius, all right? And then you have some separators, depending on the chemistry, they might get melted down such that you can trigger the internal short circuit. Or if you coat it, then you can delay the melting down of the polymers. However, for the cathode materials, essentially they are transition metal oxide or transition metal mixtures. They can thermally decompose such that oxygen can come out of the matrices and then becomes oxidizers in the system. And we all know the electrolyte, they are prone for combustion, so they are combustible, flammable. So imagine you have an environment that is of elevated temperature, and then you have the gas oxygen generated from the cathode, and you have a flammable electrolyte. They are together, you are in trouble, right? So basically, we want to understand if we could model this system if we can get some predictive way of telling whether we can operate the batteries in a reliable way and safe way before a thermal runaway gets triggered. We want to understand why certain materials has better thermal stability, etc., etc. So to do that, we turn to the literature and we see what experimentalists that are very comfortable with material science and especially the cathode materials can tell us in the literature. So this is a relatively well-cited paper looking at the thermal stability of cathode materials. And this type of cathode materials is called the nickel, manganese, and cobalt. And you can have different compositions in terms of the relative composition of the three elements. Basically, you can see that they would thermally decompose at different temperatures, but there is also shared trend. For example, the materials by design, they should be layered structures such that lithium can go and ions can go in and out of the lattice to storage energy and electricity, right? As we increase the temperature, the lattice would transform eventually to the rock salt phase. And this step, depending on the chemistry, would happen at different temperatures, but the shared trend is that you need to have a 3 stages decomposition depending on the temperature. And probably this actual composition will delay it in certain ways. This is what the material scientists can tell us in the literature. For combustion scientists, we can also conduct experiment by taking scratching out of these cathode materials from batteries and do experiment in the so-called scanning differential calorimetry. So basically, it's a device that you put the materials and use carrier gas to heat it up at a certain heating rate. And if we have thermal decompositions that would release heat, you will see the peaks in the heat flow. And generally speaking, because we can assume that each peak corresponds to one reaction, we can do this experiment at different heating rates such that we can extract the activation energy and from a suite of experiments. And this is the majority of the community has been doing. And the appearance of these 3 peaks also correlate very well with the material scientists' view that we do have decomposition in 3 stages. However, in the same experiment did by the same group from the combustion community, we noticed that for the NMC 622 materials, we can actually only observe 2 peaks. However, we know that there are 3 reactions that should be modeled. Therefore, the naive way is to try to fit 3 peaks to the 2-peak measurement. Well, you can always do that because it's just a data fitting. However, it's unphysical. You can take a look at the second, this purple-colored shaded area. Basically, what this means is that the second stage decomposition starts to happen even before the first stage happens. So this tells us one very important lesson. For any data-driven modeling approaches, you could fit to the model or to the data very well. However, you could be unphysical, right, which would prohibit you from having a reasonable and predictive model. So the way we try to deal with it is that how about we still maintain the data-driven modeling approach. However, we want to embed physics into the modeling approach such that we can be confident about the fitted model that we have. And the way we embed physics is through this framework called chemical reaction neural network, developed by my group about 4 years ago. So essentially, this is what happens, is we can write the general format of chemical reactions. And we know that for general chemistry, we need to comply with the law of mass action. And this is how law of mass action is written. And we can linearize this term and then have an activation exponential function in the front. So mathematically, this is identical. But then if we take a look at this and try to explain it in terms of a graph, then we immediately see this is something familiar to us in the neural network world. Basically, you have a linear combination to this neuron and then do a nonlinear activation, and then you can have another linear transformation into the output layers. So if you have experience with neural networks, you can identify there are many parameters, biases, activation function, etc. But even if you don't understand neural networks, you understand the physical world, you actually would figure out all the parameters can correspond to the physical meanings of the physical world. So essentially, we can utilize the machine learning framework to do the fitting. However, all the parameters that we learned are physically interpretable. They are a physical model that in the end we develop. Similarly, we can encode the temperature dependence into the framework as well to make sure that we satisfy the Arrhenius law that is also generally true for chemistry as well as for these battery systems. So in the end, we can put everything together so that we can model a set of reactions that can describe what's happening in the system given some experimental observations. And what's good about this is that we do not need to assume what type of reactions we have, as long as they are generally applicable for the law of mass action as well as Arrhenius law. So whatever you learn, the parameters are two kinds. On the hyperparameter side, you essentially learn how many species should be involved and how many reactions is enough to describe your system. And for the other connections, they are the physical parameters that would go into the physical system. So in the end, we completely open up this black box and make it a transparent box and essentially a physical model. Particularly to the applications to understand the thermal runaway of lithium-ion batteries, we can actually leverage additional physical insights that we can get from the literature, especially from the material scientists. For example, previously I told you that we identified that there are 3 stages in the thermal decomposition, and they're happening in the sequential way in 3 stages. So we can actually incorporate that information into the architecture of the neural network as well. For example, we can identify the 3 stages and in terms of the 3 reactions. And one stage, the product of the first stage needs to be the reactant for the second stage, so on and so forth. And for the experiment, I just show you with the heat flow information, that's a thermal measurement. So to incorporate that, then we can add another connection describing how the production rate of the materials correspond to the heat release from the material through this thermodynamic information. And we can model that thermodynamic parameters in addition to the chemical kinetic parameters. As a result, we would be able to come up with a physical model. And why it's so important to have a physical model is that if we do a pure data-driven model without any physical prior, we will not be confident about applying this to an unseen case. However, now that we have the physical model and everything's transparent, we could actually explore what would happen for unseen cases. And this is exactly what I'm showing you on the slide. So for the dashed lines from the literature that you previously already see that they managed to fit to a 2-peak curve, however, it's unphysical. With the CRNN approach that Ben developed applying to the battery case is that not only we can be more physical, but also quantitatively, it also agree very well with what is experienced and observed by the experimentalists on the critical windows that we have the 3 stages of the thermal decomposition. And this is really the advantage of embedding physics into the machine learning framework. After that, we would be able to apply this to a wide range of materials to understand why certain materials is more stable thermally compared to other materials. For example, we can compare the trend of different nickel content and make sense of why a higher nickel content is less thermally stable because of the increase in the activation energy, etc., etc. and be able to understand why single crystals is more stable than polycrystals. We were very happy about it until we realized that across the literature, in addition to that single group that did a lot of experiment, there are also other people trying to repeat the same experiment following the same procedure. However, at their best, this is across the world all the experimental group can get. We will see that, well, generally we have the same trend. Some peaks happen at the same temperature, but not all the peaks, right? And sometimes you have 2 peaks, sometimes you have 3 peaks, etc., etc. They all claim to follow exactly the same procedure and utilizing the same material. That actually showed that the experimental data itself is highly uncertain with some experimental errors and uncertainties. So our model needs to be able to accommodate a wide variation in terms of all the data. We presume they are true, but they have uncertainties. So we develop a further module to model the uncertainties in the experimental data, such that our model would be able to capture the uncertainties and be able to give us an ensemble prediction of all the possible scenarios, taking into consideration of the variations in the chemical kinetic parameters. So now we are ready to apply this not only to the cathode materials, but also to other materials such as the separator, the electrolyte, the anode, the SEI, etc., etc. So we dive into the literature and see what are the available data set. And this is what we got. Essentially, we have a very nice set of experiment. They did the experiment as much as they could. For example, if they could have clean experiment with the electrolyte, they can just take the electrolyte, put it in the oven, put it in the DSC and run it. But there are other cases, such as the SEI layer, there's not possible for them to peel that off. So they have to take the entire electrode to the devices, right? So I'm skipping a lot of the details, but essentially sometimes we can directly model the component. Sometimes we need to consider that the system is not clean enough, so we need to do it stage-wise. As a result, you have to trust me, as a result, we are able to model the individual reactions associated with the individual components, as well as the interactions between different components. And now it's time to validate the model, but also try to explain, try to comprehend the single cell level experiment. So previously I talked about that we can peel off the materials and look at the individual materials on the component level. And now we are ready to move forward by throwing one battery into the reactors and try to operate it and try to heat it up until thermal runaway happens and see if we can capture the dynamics well. So this is typically how a reaction would work. It's called a heat, wait, seek process. You cannot see it, but actually this figure is keeping track of the time you spend, the battery spent in the reaction chamber, and the temperature of the cell. So the environment, you can control the heating rate and the environment inside the chamber. And the battery is heated at a relatively slow heating rate. And after you heat it, you wait a few minutes and to see if the temperature changes. If the temperature doesn't change above your setting temperature, you can continue the heating process. And you can see that after, from point 1 to 2, at 2, after you stop heating the batteries, the battery will start self-heating. And this is the trigger of heat release processes. And if you wait long enough time, such heat accumulation and self-heating would eventually trigger the internal short circuit by the melting down of the polymers, separators, and then you see the battery catches fire. And all these, because now we don't have external heating, so it's an adiabatic environment. This whole process captures this thermal runaway of the batteries. And eventually it would cool down after everything's burned off. All right, so this whole process is done in the experimental setup called ARC, and we can try to capture the dynamic procedures via this quite a complicated diagram. And then we can get as much as possible all the parameters that describe the mass and internal short circuit, etc. And we utilize the model that I just described to you that Ben developed from the CRNN approach to model the thermal runaway. And here is a very busy plot, but I'll try my best to explain to you how we take our full model and try to understand the dynamics that we observe in the cell level experiments. And to highlight the importance of making sense or considering all the uncertainties associated with single components. For example, now you see this is an experimental measurement, and basically it's done across different chemistries, etc., etc. Basically, this experiment is to show you that, well, the onset of ignition, the onset of a thermal runaway depends on the cathode chemistry. However, if you recall the figure I just showed you, actually at this relatively low temperature, T is roughly 80 Celsius, actually you shouldn't have any dependence on the cathode. It's purely determined by the solid-state electrolyte. Solely developed by the SEI layer. So if you do it in the deterministic way, you wouldn't be able to capture the influence because in your model, nothing should depend on the cathode. And this is not a single case. If you look at other metrics, such as the onset of thermal runaway, as well as the maximum temperature, all of them, we cannot capture the dependence on the cathode chemistry. This tells us the importance of considering the variations in the experiment and the result of deterministically model the chemical kinetics. Now that we are able to capture the uncertainty, we would also be able to simulate all the cases with all the possible chemical kinetics. So this is what Ben did, is to do a lot of random samples of the possible chemical models so that in the end we have an ensemble of the predicted dynamics of a single cell putting into this ARC experiment. And the dark green is what we get. We can roughly capture the dynamics and especially the variation across the literature, why across different chemistry we have different sensitivities in the three matrices, right? So the take-home message we want to have is that due to the complexity of battery materials, sometimes it can due to the labeling of the manufacturers, but most of the time it's due to the usage of the batteries. You don't have a pure materials. You don't have all the same SEI layers, etc., etc. You do have a lot of experiment uncertainty. So when you come up with the chemical model to describe the dynamics, you actually need to consider such uncertainty. If you only take the deterministic one from a single experiment, you will not be able to capture the variations that we will observe in the experiments. So in this part, a brief summary is that I try to demonstrate to you how we can incorporate the physical intuition or physical evidence across the literature and try to use that to inform how we design our machine learning framework. And collectively, we can build individual models to describe different components of lithium-ion batteries. And then we can put them together to describe on the cell level how a battery would behave under thermal abuse. And I introduced to you this Bayesian CRNN, which is a framework that can deal with not only the chemical reactions inside the batteries, but it has this promise of dealing with the general chemical system. So I just showed you a story on the inverse modeling side, and then now I'm going to show you how we can accelerate the CFD calculations and try to do the predictions for a system level for energy conversion system, and particularly for combustors. We're interested in the terminology called the digital twin, and many of you might have already heard about it. And depending on the area, the definition could be slightly different. So in combustion community, essentially what we want to have is that in the physical world, we want to be able to visualize and model a real combustor. And the digital twin is a a digital replica of that system. We want to be able to visualize the flame inside the system. We want to be able to measure everywhere how the emissions goes, such that we can optimize the system by optimizing the design or the operations to enhance the safety of the combustors, to enhance the thermal efficiency of the combustors, as well as to minimize the pollutions, emissions from the combustors. And the key message is that how we can utilize the world from both simulations, that is CFD, and later on you will see these very expensive CFDs, as well as some measurements, but with a caveat that it's a very hot environment. It's impossible for you to stick into the sensors, into the combustors, and measure every component you want to measure, right? So basically, how we can combine the information from both worlds and be able to describe the combustor systems with the help maybe from some intuitions or reduce order analysis that we could have on the theoretical side. So the key challenges we're trying to overcome are the threefold. The first of all, for a real combustor, you have very complicated fuels, and sometimes the fuel will get injected at different stages and different timing. And you can have air coming into the system at different locations, at different velocities, etc. So essentially, you are having a relatively high dimensional space for the operations. When we say high, it's about order of 10 parameters that you can control, right? And in order to visualize them, to have all the information, well, one way of doing it is to conduct computational fluid dynamics. But now we are talking about a highly turbulent flow that we need to resolve the level maybe in micrometers, and we need to resolve a combustor on the level of meters, right? And then we need to resolve in time and space. We are talking about millions of grid points to resolve such CFDs, right? So you can imagine the availability of high fidelity simulations will be quite limited. And eventually you can say, well, I can turn to the help from experiments. However, as I mentioned, it's very unlikely for you to be able to stick a sensor to measure the flame temperature. It's gonna burn down. And for emissions inside the reactors, it's impossible for you to measure that. Sometimes you get measurement on the surface near the wall. Sometimes you can have a single measurement at the outlet, but it's impossible for you to resolve every quantity of interest by purely measuring those. All right, so in the next 10 to 15 minutes, I'm going to explain to you, show you 3 quick cases to demonstrate how we can combine the best from the both worlds to help us build a field reconstruction tool to describe this combustor system. The first problem is to say if we know how we want to operate our system, can we bypass the CFD and try to predict what's going on inside the combustor by purely specifying the parameters we run our reactors at? And then the second approach is that if we can have some measurements for some quantity of interest, are we able to utilize that information to infer the distribution of other quantities of interest without simulating them or measuring them? And the third is that, say, if I don't have complete information of either of them, can I bring them together and have a universal description of the system such that I can do data fusion to minimize the requirement on the data I need to have? And the example I'm going to show you is one of them. I will show you a couple. To illustrate the complexity of the system, I can describe a little bit for this. It's called a great furnace, is to do the biomass combustion. And this case is evaluated by my postdoc, Lin Zheng. So this is essentially what it is. You have the solid fuel, in this case will be biomass, that is transported utilizing this conveyor belt, and you have hot gas, hot air blowing it such that the biomass will have thermal decomposed and then have some gaseous species, flammable gaseous, combustible gaseous species after the pyrolysis. And here in this case, you have secondary air and you can further combust the gaseous species, and eventually goes out of the system, right? So like I said, you have a lot of places to blow the air. You have a lot of operations. So in the end, we have actually 11-dimensional parameters that we need to operate in the real operation. And the physics and the chemistry are very complicated. And you can try to do a 3D CFD about it, but it's going to be very, very expensive. All right, and our end goal is that, say, now I have a random combination for the operation, so the 11 parameters. I just want to know, without doing the CFD, am I able to know the temperature distribution, how the flame would look like inside my reactors? And this is what we generally do. Skipping a lot of the details, essentially what we are trying to do is leverage the physical constraint or physical intuitions by the system. Because we know that the pyrolysis of the fuel bed is going to determine the gas phase species as well as the temperature distribution. So modeling the fuel bed and the temperature distribution after the pyrolysis is very important, right? And inside the combustors, there's the gas phase reactions. So we can actually combine the simulation. It's a relatively simple 1D simulation for the fuel bed to get some characteristic out of it and build this into the whole framework and blend in more information along the pipeline. So in this case, we do not need to simulate everything all at once for 3D. Instead, we could leverage some of the lower fidelity, one-dimensional information to build the overall structure and utilize the 3D information, a relatively smaller amount, to do the fine-tune of the models. And I'm going to skip the details, but show you this is what we are able to achieve. So essentially, after we are able to build this system, we would be able to infer or construct the temperature distribution, 3-dimensional temperature distribution inside the combustor, right? If you were to do the CFD, this would take several days on the supercomputer. And now, since you are able to build a surrogate model, you can see the fidelity is relatively high compared to the ground truth. We capture all the significant features in terms of the temperature distribution, the shape of the flame, and even the strength of the flame. And this only runs as a desktop for a few seconds. So in the real operation, we want to know if we operate at a certain state, what would my flame look like? Would I have an extinction? Would I have overheated in certain areas? So you actually need to have the detailed information. And it's not possible to simulate the CFD on the fly. However, by utilizing this type of surrogate modeling, you would be able to achieve the same level of simulation to the level that you want to control it. So we now have achieved the task that we can predict what's going on in the combustor given the operation states. Right? Next, what we want to do is, can we leverage some measurement we might have to the system, although we know we will not be able to measure everything that we want to know. So this is really inspired by the mainstream machine learning for natural language processing and image processing. Essentially, if you are able to understand the system, you would be able to project it into the so-called latent space. And inside the latent space, if your model trained very well, if your latent representation is correctly trained, you would be able to differentiate different systems in the latent space. For example, for the numbers from 0 to 9, right, in the latent space, they would distribute or relatively clustered surrounding some centers. And each cluster would represent one number. This is just the illustration of things. So what we want to do is that, say, if we can have some temperature measurement, or we have velocity measurement, and basically it's from the same time measurement of the system, no matter which quantity we are looking at, essentially they're describing the same physical system. So a good representation would allow us to always pinpoint to the same representation in the latent space. And this is essentially what we are trying to do utilizing this coffee framework, is that we want to get the latent representation from the individual field such that we can use this unified system feature in the latent representation and use that to reconstruct all the other fields that we do not have measurements of. To visualize that we have successfully accomplished this, this is the visualization of the latent space. And each point corresponds to a representation from the measurement. And we can see that in the latent space, there's a natural separation of the cases. And later on, by looking at what this data actually correspond to, we notice that this separation actually depends on certain physical quantities, although it wasn't explicitly given to the data to inform it. Right? So we can separate the capacity and the equivalence ratio and the mode that we operate our parameters, our reactors. So we further apply this to a bench scale, lab scale combustion that is burning ammonia and hydrogen as the alternative fuels. So you can imagine that for the fuel injects, and you have secondary, primary air, and then you have circulation zones, et cetera, very complicated. But the good thing about this is that the CFD is validated against a real experimental measurement. And what we want to do is that, say the temperature can only get measured, and it can only get measured at the wall of the combustor. Would we be able to take the 20 measurements on the wall and infer how the major species, as well as all the pollutant-related species, how they distribute inside the combustors? And by eyeballing it, I hope you agree that the machine learning predicted ones are pretty well capturing all the important species, even for this NOx, which is a very important pollutant. And finally, we would say, what if the information I get is incomplete? I might get a single measurement from the sensors. I might know something about how I operate my system. Would I be able to process the information similar to the way I explained to you? I tell ChatGPT and I give it a picture. So this is the unified one that we can take the multi-model inputs and to get it. And the core functionality is that we want to be able to reconcile the information from both the operation parameters as well as the measurement. So to do that, we actually also try to reduce the number of simulations we need to train our model. As I mentioned, the 3D computation is really expensive, and we don't always want to simulate it to build our digital twin. We want to be able to leverage low fidelity simulations and to be more informative in that way. So the total database that we have, right, we can do roughly 300 simulations with relatively cheap way for the 2D simulations. And about 1/6 of it, we can also try to do the 3-dimensional high fidelity simulations. Okay? And we use the 2-dimensional simulations to train a neural network to describe what we can learn from the data set. And then we utilize the 3-dimensional simulation to do the fine-tune. But not only this, so there are two core functionalities we want to achieve. First one is this neural network is going to predict how the 2D distribution of certain species would look like. But after the information from the 3D, not only we will be able to expand the prediction of the 3D flow field, but also be able to capture quantities that didn't get simulated in the 2D simulations and only get simulated in the 3D simulation. And we will see how well we do in these two tasks. And essentially, the key feature is try to be able to describe the physical system, make sure that we understand what's going on in the system, make sure we understand how different quantities of interest are connected with one and another. So without talking too much on the details in the structure, you could ask later, but I want to show you what's the result that we can get. So you see in the red lines, those are the training based only on the 3D information. Say, if you want to build a neural surrogate utilizing the 3D simulation, this is what you would get for the training set, the dark red, and in your test set, basically those are the unseen cases. And you do see a drop in the performance because essentially you don't have much information. With only 48 simulations, you cannot inform this model very well. However, on the bottom, you can see that this is the case where not only we utilize the 3D simulation, but also the 288 simulations from the 2D. And we can do relatively well in both the training set as well as the testing set. Well, if you pay attention to what I just said, you will say, wouldn't that be obvious? In your 2D, you essentially throw in more information. Of course, it's going to be more informative. And I won't argue with that, but if you move on to the lower plot, you get to see that we also vary the number of 3D simulations in the training set, and while keeping the 2D, right? So you can see that with the same number of 3D, we always, by adding 2D information, is always to be better. That's obvious, and that's expected. But also, you want to pay attention to the efficiency of adding the 3D information, right? So for this case, even if you have 40 very detailed simulations, it's not going to be as informative as only having 15 3D simulations. And of course, now you would ask, then how much more expensive would the 3D simulation be compared to the 2D? So my group have told me that running a single 3D is going to be more expensive than running all of the 2D simulations, okay? So you don't lose much by adding a little bit of the 2D, but you do gain a lot. All right, so basically this is to demonstrate that by blending multi-fidelity information, we can make good use of the relatively expensive and difficult to get 3D information. And this is generally how things would behave, because previously I only show you the mean square loss. And this one, you get to see that by adding a little bit of the 2D information, you are always able to improve the predictability significantly. And compared to the ground truth, we actually did a very good job. And after we are confident that we can very successfully blend the information from multiple inputs, such as the sparse measurements, such as how we operate the system, then we can design a downstream task, essentially to guide us how we can most efficiently run our combustors. Sometimes it's decided by the indicators such as the CO, which is the indicator about how efficient we run the combustion is, and also the indicator from NO, which is a very strong emission, which is a pollutant that we want to eliminate as much as possible. So the take home on this page is really the importance of adding the 2D information and having a holistic view of that. What I'm showing you here is that on the top, basically you can also build a surrogate using the naive neural network and try to learn from the 3D, and then predict how the emissions of CO and NO would look like based on the 3D surrogate. On the bottom is the case that we want to build a surrogate based on the unified representation in the latent space. What's interesting, the general trend is that we always do better here, but what's interesting is actually the last column, because the NO simulation was not included in the 2D simulation. So in the 2D, we have certain species, but we never simulated a 3D. So you can imagine all the information on the NO is from the 3D simulation. However, by knowing something about other species through the 2Ds, we can actually improve the performance in predicting NO. So this tells us, even though you do not know the quantity of interest directly, by knowing some other things that can give you another point of view of the system is also very helpful. So machine learning will help us to do the task. Even if I cannot directly measure you, I still get you the information you need to understand the system. And after that, we would be able to run the simulations really quickly. So bypassing CFD, we can do a wide scan of cases, try to minimize the emission from both CO and NO, try to tell us how we should operate our combustors. And we can then use the posterior analysis to verify it with the CFD. As you can see, the prediction is very well. With that, I would like to conclude the talk on the digital twin. Essentially, machine learning is trying to help us to take the input from multiple sources. They collectively inform us the nature of the system that we are trying to understand. So next, we are interested in be able to predict the dynamics of the system and eventually have this predictive way so that we can integrate the predictions from the digital twin and then inform us how we should control our parameters, how we should run our combustion, such that we can have a control loop to leverage the significant reduction in the computational time of the digital twin compared to the CFD solvers. And today, I mainly focus my talk on the scientific machine learning part because I felt that this was not something I covered significantly in the talk I gave 2 years ago. But still, we have the experimental component. Now that I have many of my experimentalists sitting in the audience, taking the information, taking the knowledge we have from the fundamental combustion science, we can tailor the applications in terms of making materials, such as battery materials. The recent MIT news and the video about our group's work focuses on that, burning things to make things. All right? And on the other side, we are also developing solid fuel and alternative fuel to try to mitigate emissions by the combustion of fossil fuels. And although with the time, I can only share some of the work, I do have a wonderful team that is sitting in the audience that contribute to all the 3 thrusts in the group. And all the audience are very welcome to connect to my wonderful students and staff and postdocs to hear more about the research progress in the group. With that, I thank you for your attention, and I would happy to answer any questions you might have.
Okay, thank you, Celia, for a very informative seminar. We have time for some Q&As. If you have a question, please raise your hand and wait for me to hand you the mic. Okay, Yaris.
Do you want to use the mic? Yeah. Given your comment about how expensive one high-fidelity simulation is compared to 2D, I guess I wanted to see on there, how well do you do with just 2D data? And then what about if I can only do one 3D simulation? You showed efficiency, but you started at like 15, and you already said that one 3D simulation is more expensive than all the 2D simulations. So what do I get if I can only afford one 3D simulation? Do you have data that goes back to there? And I guess I'd love to see what just 2D data does in terms of how accurate am I?
Right, so the comment on that is for 2D, well, then for some species that you don't have simulation in the 2D, then of course you cannot simulate them, right? For example, the NO was not included in the 2D simulation.
But that's a different thing than 2D versus 3D. That's a choice,
right? That's the model you choose to do.
I could have done simulation with NO that in 2D.
Exactly.
So I guess I want to see how well I do with that.
Right. So I don't have the result there, but you could also think there are cases I train only on the 3D, right, for those cases as well. So we would always be able to train it. And for the 2D, since the computational cost isn't that high, we could incorporate more data into it. So potentially you could have even higher accuracy because you can afford to do more simulations. Then, of course, the question is, well, how many 3D is needed? Then I think probably the best way to do it is just to keep on adding new things and see how sensitive it is to that, right? For example, I showed you that by adding only 15, it's already very helpful. But of course, I would imagine at the very beginning, adding 1 and adding 2, and every single one would matter, will help me enhance my performance significantly.
But the biggest gain is for the first one,
I think so.
and then a smaller one for the second, and so on. It's a law of diminishing returns.
Yes.
Yeah.
Maybe I can add a small question somewhat related to the current question. So in the first part of your seminar, you talked about the reaction network, neural network, and extracting some fundamental data regarding the reaction, activation energy, and so on from experimental data. And you embedded the physics of the kinetics into the model in order to get better results. In the second part, you talked about the digital twin. You seem to have left the physics out, governing equations out, and relied largely on data. Could you think of a way of bringing in some of the physics back into the digital twin to again address issues of how much data you need and whether you only can rely on 2D or 3D? Can you bring back some of the conservation equations, for instance, into the mix?
Yes, that's a wonderful question. So this is actually the heart of scientific machine learning, right? In addition to machine learning, where does the science come into play? So to comment on that, the first part, we actually hard-coded the science into the architecture. In the second part, I didn't dive into the details, but you could imagine we still utilize certain things. For example, in the first example I showed you, I was like, the fuel bed is very important. Then we actually need to nail the one-dimensional temperature distribution on that. And we utilize that as one of the loss terms in our training, right? So we are saying, well, basically it says you need to get this trend correctly. And some other places we could also try to say, well, the flame has certain shape, so we can assign a distribution of things. And for other cases, if we think mass conservation is very important, we can also add in the regularization that you need to calculate the mass at each grid point and make sure they sum up to be 1, etc. So those are the things you can add. So sometimes it's the architecture you design it in a certain way already have the physical constraint embedded, such that you need to nail down the first 1D, then the 2D, then fine-tune with the 3D. Sometimes it's more explicitly embedded in the loss function that you design.
Okay, other questions? Maybe I'll ask another one while they're thinking about it. So in the digital twin, and I go back to the idea of bringing in some of the physics. For instance, if you're looking at the biomass combustible versus the ammonia combustion system, how would you start your neural network training based on, structuring the neural network around the nature of the fuel you're burning and the system you're burning it in?
Right. So for digital twin, essentially, it's a replica of the physical system. So if you completely change to a new system, or even geometry-wise is different, I don't think there's much you can directly inherit to the new system. So that's the limitation, I would say. But the general framework, how we can embed the input into the framework, or how we should design the case that we can have a universal representation, I think that knowledge can be transferred. But what we really also want to do in future is to modularize the digital twin, such that if now we have a system, say we have 2 burners at the same time, of course, it's not going to just be the additive of the 2. There will be interactions, but maybe the next step that you understand the interaction, that step, you don't need to have a lot of data to further inform you. You can quickly converge to the correct solution. That's probably what we can do.
Okay.
Yeah, I think great talk, by the way. Something that would be really interesting is if you actually showed the computational costs for 1D, 2D, and 3D, and just make a comparison to see if it's actually worth doing a 3D high-fidelity simulation run on it.
Right. But the end goal is that for the actual one, we need a 3D prediction. So we have to go there anyways. And from the 2D and directly go to the 3D, then that's almost impossible.
Yeah. So what I mean is whether there are significant computational benefits for doing multi-fidelity in this case. Yeah.
Right. It's already significantly helpful by comparing the 2D plus the 15 3D and the 40 3D. Right. That is already very clear. Yeah. It's like orders or 2 orders of magnitude reduction in the computational time.
Okay.
Thank you very much. Very interesting talk. So I have a question. You mentioned enforcing the mass conservation. I was wondering if you also try to do other like momentum conservation or energy conservation, because usually, at least from my experience, when it goes to like 3D, as you mentioned, like with maybe 10 million cells or 100 million cells, it's really hard to conserve energy or momentum if you're doing scientific machine learning.
Right. I would say really, those things can be considered, and but it also depends on the application, right? For this case, with the fidelity that you eventually reach, right? For example, it's the Reynolds average number. So for all of these, compared to the DNS, first of all, you cannot do DNS, but also compared to the so-called ground truth, it's already a lot of error. But of course, mass and energy, they should be conserved by the design of the numerical solver and the governing equations, that's for sure. But the added value of actually getting all the mass conserved, for engineering application is not that important. The general shape of it, right? And for engineering design, we also have a safety factor. So probably for temperature, you don't need to get it dead on. You're probably within 50 Celsius, you would say you did a very good job, but you are not gonna melt down your burner or furnace. So that's the fidelity, the overall fidelity the engineers would want, right? There's always a balance between the performance and the effort you need to pay in terms of doing the training or preparing the data to that. Yeah.
Okay, one last question. All right, well, let's thank Celia again.
Thank you.